on my own behalf, I welcome Dr. Ajay Kumarji to this session of a guest lecture to be delivered by him. And I'm sure the lecture, has been arranged by Dr. Manoj Kumar Singh, will certainly be very beneficial for our research scholar as well for faculty members who are working in the field of nuclear physics. And for my colleagues, I would like to tell Dr. Ajay Kumar actually has been working in the field of fusion and fission dynamics, and he has published so many papers in this field. And actually, he is studying of heavy ion fusion fission dynamics. So we should listen him, and I think his lecture is going to be very beneficial for all of us. So I would now request to Dr. Ajay Kumarji to proceed on, and please start, keeping in mind that we have only 30 minutes and 5 or 10 minutes for discussion. So this is the restriction from actually the link side. So please be just be brief and try to cover up within 30 or 35 minutes. So with these words, I would request you to please proceed on. Thank you very much.
Thank you, sir. Thank you very much, and I will keep in mind your instructions. So, Manoj, should I start?
Yeah, sure, sir.
Okay. So, good afternoon, dear students and honorable faculty members of GLA Mathura. So, this topic I especially prepared for students, those who are studying in graduation and post-graduation level. And in this topic, we will talk about
Can you
radiation
please
interaction.
speak loudly, please?
Okay. So, am I audible now?
Yeah,
Is
yeah,
it
I
good?
think it's
Okay,
okay. Okay, sir.
okay.
Yeah. So
Now it's okay.
I have prepared this lecture especially for UG and PG students, those who are taking any paper of nuclear physics. So in this paper, in this talk, we will discuss about the radiation interaction with material, how it interacts, and it's very basic lecture so that you could get. And my email ID is given in the presentation. So if you have any query, you can ask after I conclude, or you can put your questions after the talk. So I'm going to start presentation. PPT.
No, sir, it's not appearing till now.
Get it from. Oh, share the screen. Okay, I think now we should see. Screen. Is it coming now?
No, sir, not yet. सर स्क्रीन शेयर वाले ऑप्शन पे क्लिक करिए फिर वो आ जाएगा.
Okay. So.
Unmute कर दो, unmute.
Is it okay?
No, sir, no.
Okay, it's okay.
स्क्रीन सर आप हाँ स्क्रीन सर आपकी नहीं दिख रही है सर. सर पहले आप उसको सिस्टम पे खोल लीजिए स्क्रीन को, फिर शेयर करिए, फिर अपने आप आ जाएगा.
It is open on my system.
So स्क्रीन शेयर वाले पे सर क्लिक करिए.
It is open. Okay, so just tell me now. Can you see it now?
No sir, ये आपके विंडो पे भी सर दिख जाएगी अगर जैसे.
Can you see? Can you see that?
हाँ सर अभी सर शेयरिंग पे आ रहा है. हाँ सर क्लियर आ गया सर.
आ गया. Okay.
Okay. Thank you very much.
Okay.
So this is radiation interaction with matter, and let's start it formally. So if you go on the objective of this lecture, so the basic aim of this talk is to familiarize students with the physics of events that will take place when photons, charged particles, and neutrons interact with the material or matter. And the concepts such as mass density, attenuation coefficient, stopping power, and range. So I hope you all are familiar with this picture. So if you see the first segment, this one, so you see alpha particle, beta, gamma, and the fourth one is neutrons. So we are going to talk about these particles like alpha particle, how it behaves when it enters somewhere in the material, how beta behaves, gamma behaves, or neutron behaves. But there is a fundamental difference between all these particles. If you see alpha and beta, so both corresponds to the charged particle community, but alpha is positive and much heavier than beta particle. If we talk about gamma, so again it's a massless particle. If you talk about a neutron, so it's a chargeless particle. So their process of interacting material is completely different than charged particles. And this is the diagram which tells you about the frequency or energy of particular radiation starting from AM radio to X-ray or gamma rays. So what about interaction? Whenever a beam of radiation, when we say beam of radiation, it means a linear beam of particles, radiation particles. Like if you say of alpha, so you can have 10 to the power 6, 10 to the power 7 particles per second of alpha particle. So that is called a beam. So when a beam of radiation of any kind penetrates matter of radiation, may be absorbed, or there is a possibility it may be scattered. Scattering means the game you see in billiards. So it's a simple example of billiards, or we play marbles. So it's a case of scattering. And in some cases, it may pass straight forward. There is no interaction. So there may be process of absorption. There is a possibility of scattering, which can be described and explained in terms of interaction between particles. Particles in the beam of radiation strike particles in the material and are either stopped or scattered. So this is overall about the interaction of particles. There is few possibilities, whether it's a complete stoppage or continuous processing inside the material. But ultimately there will be somewhere a stopping part. So we will briefly discuss those kind of interaction. So I made this lecture in three segments. Firstly, I will discuss about the charged particle interaction, then we will go for photon interaction, then we will go for neutron interaction. So if we talk about charged particle, so we will having alpha, higher mass, we will talk about beta. So they will represent to all positive community particles, and then we will talk about photon and neutrons. So what are the possibilities if you talk about charged particle or photons or neutrons? So there are two broad kind of process by which a particle traveling through matter can lose its energy. In the first kind, a gradual process, like you are hitting the material continuously, slowly, you are losing your energy inside the material slowly, very slowly. Say sometimes it may be 50,000 interactions between atoms of the material. So that category comes when your charged particle interaction takes place. If you talk about the second category, like photons, so it's a catastrophic type of event. So in that case, there is a possibility that there may be nothing, or there may be a single or more than more than 2-3 collision, and the particle is completely stopped. So that is the behavior of photon interaction. The motion of charged particles through matter is characterized by residual energy loss, and photon is all or nothing. So this is a broad difference between charged particle interaction versus photon. So again I am summarized. Charged particle is a slow process. Gradually it will decay its energy inside the material. It will stop completely. And in case of photons, it will be a single shot or nothing type. So we start for charged particle. So obviously, it will see a Coulomb barrier if your incident particle is positively charged like alpha. So you will see a repulsion from nucleus. If you have a negative charged particle like electron, you will see a attraction. So charged particle interaction has four categories broadly: ionization, excitation, Bremsstrahlung, Cherenkov radiation. So ionization is good for both alphas and betas. Excitation is good for all alphas and betas. Bremsstrahlung is very crucial in case of especially for betas. Similarly, Cherenkov is good for primarily betas. So we will talk step by step about these four processes. There is no, I don't think there is any need of discussion for ionization and excitation. So I will just show you one slide, next slide. So this is the simple process of excitation and ionization. But you need certain amount of energy so that you could excite anything or ionize. So if you want to get it ionized, so you should have that kind of energy so that the ionization threshold could be reach out, or you should have certain amount of energy so that you could push your electron from one cell to another cell. If you don't have that quantum, you cannot. So these are two processes done by child particle when it interacts with the material. So one possibility, there may be excitation. Second possibility, there may be ionization. The third one, that is good for beta especially, known as Bremsstrahlung. So it's a German word. So if you convert in English, so the meaning of Bremsstrahlung is breaking radiation. So as you see, one electron is coming in the vicinity of nucleus, and due to the force I showed in the previous slide, Fq1, Q2 R square, it has slight deflection towards the nucleus. And that deflection makes a decrease in energy of this electron, and that loss of energy comes out in terms of a photon. So this process is known as Bremsstrahlung process. So this is the third kind of interaction of charged particle. Then I hope you heard about delta rays. So delta rays, when my alpha particle moves inside a material, and I mentioned that there is a possibility of ionization. So if it ionizes the material, and you see there are positive ions and electrons. So if you have sufficiently large kinetic energy of electrons after the ionization process, so these electrons can be used to get additional ionization in the material. So it's a two-way process. See it clearly. Your alpha is coming inside the material. It ionizes your material. You see positive, negative, and these electrons are so much energetic electrons that they are again capable to do ionization. So you see another ladder. So this electron is going to do ionization. So two process of ionization is going on due to just single interaction of charged particle. But this is only possible, this is a special case, when your electrons are having sufficient energy to ionize that medium. In that case, those are known as delta rays. Next category of radiation interaction of charged particle is through Cherenkov radiation. So if your particle is very high energy carrying particle, if it is having speed of more than light inside the material, so in mathematics, if I say if the velocity is c by n, where n is the refractive index of the material, so you see this background like when you see a boat traveling inside the river faster than the speed of water. So you say the bows, so similar kind of bows you see when your Cherenkov radiation shoot the material. Now we come on the terms we use when charged particle interacts with the material. So one term I believe you all heard about range. So here is the discrimination when we talk about charged particle or electrons or beta particles. So you see, this is the range. Range means if you enter in this material in this square shaped yellow box, so you see it is a zigzag one and it is longer one. But if you see the alpha one, so alpha terminates at this point. You see this is small distance, but beta has a longer distance. So you see why it is not deflecting. It's a straight one, alpha almost, because it's a heavier particle. So it's like elephant and the lightweight animal. So the beta one is a lightweight particle, so it goes very far comparative to alpha, and it has a zigzag path. So this is known as range, how much you travel inside the material till the time your energy is completely zero. So range of alpha particle is less comparative to beta particle, but the path is straight comparatively to the beta particles. So then we talk about the stopping power. So stopping, as we know the meaning of the stopping, when you enter in the material, so somewhere you have to stop. So there is a term linear stopping. So linear stopping of the material is SL, L for linear, dE by dx. So it's simple mathematics. Energy loss per unit distance, and minus sign is representing that you are continuously losing the energy as soon as you are going inside the material. So you see this curve between d by dx versus depth. So here you see that it goes on, the energy loss is continuously varying, and it is going at the highest at one point, this. So you can ask why the energy loss is maximum at the maximum distance at this point. So the point is, as I mentioned earlier, that the charged particle interacts gradually. It imparts very little amount in its initial collisions. But at one stage, it feels that it is now almost impossible to move further. So at a certain distance, it imposes its total kinetic energy to the material, and it drops out, and it comes at the halt. That is, this distance from 0 to this point is known as range. But you see, it's not a perpendicular structure. It is have some kind of variation. So I'm going to explain why you see this kind of variation. So you see another picture. The y-axis of this curve shows fraction of incident particle left, right? So one means you can say that at this point you have, suppose, 100 particles in the beam. So you have all 100 points in the beam material, and you see as you travel inside the material, so you come up to this point, and you are gradually decreasing your particle incident particles, and at this point you are almost zero. You don't have any particle in your incident beam. But you see, there is not a perpendicular one like this. And I mentioned that this variation means if I put a perpendicular from here, so it should be like this, but there is a variation known as staggering. So I always tell to my students that don't remember it by staggering, just remember by struggling, because you are shooting 1,000 particles. I said 10 to the power 7 particles per second by accelerator. So all 10 to the power 7 are not going to interact in the same way. It's a statistical process. So if I say 10, for example, 10 alpha particles, same kinetic energy, but they are not going to interact with the material in the same kind of way. So few may be stopping little earlier, few may be going little further. So that kind of fluctuation from the mean position is known as stacking, and that is just by the nature. You cannot restrict all 10 that they should behave in the same way, because this is out of control thing. They are just centered in the material, so it's a random process. They can behave, certain may stop a little bit earlier, certain may be further. So that is the variation known as stacking. Then we come on a ratio which tells about the energy loss due to radiation, and another is radiation due to ionization. So when I say loss due to radiation is through the Bremner-Stirling process, and when I say loss due to ionization, so it is simple ionization process. So the ratio at relativistic energy between radiation stopping versus ionization energy is equal to ZE by E dash, where E dash is a constant equal to 800 MeV, and Z is the atomic number of that material, and E is the incident energy of the incident alpha particles or any kind of charged particle you are using. So that ratio tells you about the value of this ratio. And if you go further, so there is a critical term of critical energy represented by EC. So you see EC is equal to E dash by Z. And as I mentioned, E dash is a constant equal to 800 keV. And Z is the material atomic number. So what is the physical significance of critical energy? So if you shoot your incident particle with a critical energy, so it means that your process of radiation and ionization will carry equal amount of energy loss. So the kinetic energy at which energy loss by radiation equals the energy loss by collision is called the critical energy. So this is the meaning of critical energy. If you have equal loss among between radiation and ionization, so that incident energy is known as critical energy. Another quantity of interest is the radiation length. So radiation length is known at the distance where your energy is reduced with a factor of 0.37 corresponding to the original incident energy. So that length of material is known as radiation of length. So I hope it should be very clear to all of you. Now we come to the second part of the talk, how photon interact with the material. So I got this picture, and the bottom line sentence is very clear about the mechanism, how it governs with material. So you see, photon absorbed or scattered or out of beam. So we all know where it is absorbed. You see, in this case, you shoot a gamma, you shoot a photon, there is a material, you are getting an electron. So everybody knows this is photoelectric effect. Then you come, you shoot a photon, there is an electron, you are getting scattered. So this is second condition, so known Compton effect. Then you see out of the beam, there is no photon, means you have electron, you have a positron. So you see, it's a case of pair production. Again, I want to clarify one thing, that all these things are energy dependent also. You cannot expect this at any energy, you cannot expect this at any energy, and especially this guy cannot be at an energy. So we will take a few examples one by one of them, and you will be able to understand clearly. So you see, this is an example of Compton scattering. You hit a weakly bound electron by photon, and there is a distribution of energy between electron, and definitely your incident photon is missing energy, and you are getting this formula. This is the kinetic energy, so all of you know. So we will not go in detail of this. This is very critical. You should understand this thing. When you hit the electron with incident photon, so suppose you are shooting your photon with an energy 0.8 MeV. So you see your electron is carrying something like 0.55 MeV of energy out of this 0.8 MeV. So this is the maximum amount of energy carried by that electron, right? So this point where it is getting maximum energy is known as Compton edge. In this case, it is 1.25. So you see, it is something 1.15. So the maximum energy carried by the electron is known as Compton edge. Similarly, we have the picture of photoelectric effect. So always remember that in photoelectric effect, it is the always inside electron, which is the most preferred electron taken by the photon. So you take out this and you have electron and you have a work function. And here I just showed that you cannot shoot any wavelength. You need to shoot a wavelength of above threshold so that you could get the electron from the surface. Then there is a picture, you see, if you plot a curve between incident photon energy versus attenuation coefficient. I will come on the attenuation coefficient. So you see, there are certain edges like K, L, M. So this is corresponding to your K shell ejection through photoelectric, electron ejection through photoelectric from L shell. So you see, as you have higher energy, so you can get the innermost electron. So the K shell one, so it shows a peak because here you need a clear quanta equivalent to the K shell energy required to eject out the electron. If you go for little bit lower energy, so definitely you don't have that quanta which could eject the electron from K shell. So definitely you will go to the upper level. So your energy is decreasing in this side. So you go for L, then you go for M if you have less than this one. So this is about the absorption. So these are known as absorption edges through photoelectric effect. Then there is a Rayleigh scattering. So Rayleigh scattering is a process we know, we see our sky blue due to Rayleigh scattering. So in Rayleigh scattering, photon interacts simply with the whole atom, and the atom is slightly recoiled and the leaving the scattered photon with a slightly smaller energy. So this is called Rayleigh scattering, and this is responsible for the blueness of the sky. Then you see the process of pair production. So if we talk about pair production process, so pair production process, you see it cannot happen without the presence of nucleus. So for this, definitely you need a nucleus. Why? Because if you don't have a nucleus, so you cannot conserve, you cannot take care of your conservation laws. So in the presence of a nucleus, you interact with the material and you see the electron and position. But be careful. Here you cannot do with any energy. So if you remember, you have as a outcome of this reaction each particle electron or positron with a 511 keV. So that means 511 plus 511 is the minimum energy required for this process. So you need at least 1.02 MeV to see the pair production process. So next slide will explain you about the significance of incident energy. So you see, if I plot a curve between atomic number of various materials and photon energy, so you see clearly there is a clear distinction between all three processes. So you can see that you cannot see all three processes at any energy. You see your photoelectric is favorable up to this energy. So if you put a perpendicular, so you see up to this point your photoelectric effect is favorable, and after this your Compton scattering will take place. But you cannot say that now photoelectric effect has zero chance, but the competition is between photoelectric versus Compton, and after this energy the Compton will take place, it will take lead, it will be more dominating channel. But if you go beyond 1.02 MeV and if you go above 10 MeV, so then your pair production process comes in the lead role, right? So if you go for hydrogen side, so there is a possibility that you can see all three, but definitely here I can put a veto that here you cannot see pair production at least, right? So you see from this picture that incident energy has a role and the atomic number has a role in all these processes. Now we have some very easy mathematics which explain the procedure, how it travels, how it behaves. So this is the equation which explain the way of interaction of photons inside the material. So you see N0 is the initial number of photons you fire at a material, and mu L is the attenuation, linear attenuation. X is the distance travel inside the material, and N is the remaining particles of photons after traveling distance x inside the material. If I replace this mu L by a term lambda, which is known as attenuation length or mean free path, we all know. So it's a reciprocal thing. So I can replace equation 1 with the another equation n is equal to n0 e to the power minus x by lambda, where lambda is known your attenuation length. So here you can explain this that mu L has a relation between half thickness. Half thickness means the distance where my intensity remains 50% of the initial one is known half thickness. Then I can write my mu L in terms of my mass attenuation coefficient. So mu L is the linear attenuation coefficient, and if I multiply my mass attenuation coefficient with density, so this value mu m multiplied by rho is equal to linear attenuation coefficient, where rho is the density of the material. So I can write my equation 1.1 is equal to like this, and is equal to n0 e to the power mu L is replaced by mu m multiplied by rho. So this rho x is introduced intentionally, and I will show you why. So this product of rho x is known as areal density or mass per unit area. So in nuclear physics, we never talks in terms of centimeter of thickness. We talks about areal density, that it should be of microgram per centimeter square or milligram per centimeter square. So this is the concept of density thickness, and I will show you what is the utility of that in next slide. You see, this is the effect of density on attenuation. I am showing you all three slabs of same material, three samples of same material present in the same area. They are presenting the same area. You see, front area is same. The masses of all the samples are same, but what you see the density. It's totally different. This is less dense. This is little bit more dense. This is higher dense. So you see, since the density is different, but you see your this width is going small and small. So if you multiply by this XA, this is bigger, but the rho A density is less in this case. If you go in this case, so your XB is smaller, but your density is comparatively higher. And if in this case, XC is smaller, smallest one, but see the density is the highest one in this case. So you see the product is same. So the meaning here is the density thickness is the same in each case. So the three slabs will attenuate a beam of monogenetic photon by the same factor. It doesn't matter that this is low dense, this is high dense, this is highly dense, but because the density thickness is same, so the attenuation will be same. Now the last section of my talk is how neutron interacts with matter. So basically there are three processes. One in general I say scattering, one in general I say capture, one in general I say fission, one I say in general spallation. So when we talk about scattering, so scattering has mainly two things. One is elastic scattering, where you shoot your neutron on a target X and you have same thing after reaction. There is your energy is conserved, your momentum is conserved, and your particle is not at excited, your target is not at excited state. So this is a clear-cut case of elastic scattering. The neutrons are very good because they don't see the Coulomb barrier, so they can go easily up to nucleus. So they are very much interested in the nuclear interaction. In rest process, except elastic scattering, there is always change in the energy of this incident neutron. In this case, there is no loss. But in case of, when I'm saying no loss, that means at 0 degree. At 0 degree, there will be no loss in incident neutron in case of elastic scattering. Except elastic scattering, every interaction of neutron will cause energy loss in terms of incident neutron. So you see in this slide, there is a excitation. You shoot a neutron on target X, and the star, this is streak on X, shows that your target is in higher excited state, and the neutron is same with reduced energy. But you know, no system cannot be always at excited state. So this excited nucleus will come up as a gamma or neutron. But the condition for excited neutron is that you should have that kind of energy in your incident neutron that it could push your target up to a certain class. If you don't have that energy, so your nucleus cannot reach to that excited state. So that's the scattering, inelastic scattering example, and capture reaction example. This one is a typical example of fission, where your heavy nucleus is bombard with neutrons, and it is divided in equivalent of masses of almost similar masses, and they again go for a fission process because they are not stable, so they emit out neutrons. So this is a kind of third interaction of neutron with nucleus. So this is, I think, from my side, and now you all are welcome for questions, because I, as per the guideline of Professor Gupta, I took care of his instruction and try to finish in 30 minutes, I think. Manoj can
Yeah.
help. So
Yeah.
the session is open for questions.
Yeah. Thank you, sir. Thank you, sir. Sir,
I hope I
there.
was audible. I was audible to all.
Yeah, there was one student from BTech, Nidhi Kulshrestha. He want to ask some questions. So, Nidhi,
Yes.
please, you can ask.
Hello,
Yes,
am I
Nidhi.
audible?
Yes.
First of all, I want to wish a very beautiful noon to all of my professors and our honorable guests, sir. My question is that, what are the sources of Bremsstrahlung?
This is the only source. This is the only source. When you have a, see, in the beginning I mentioned, if you go, I'm just for you, I'm going back for you. So I mentioned that if we talk about 4 processes of charged particles, so you see, can you see this? So Bremsstrahlung is primarily for betas. I cannot say that it is not good for alphas, but you can see if you shoot your betas or electrons, so your de-acceleration is there, right? So you shoot any charged particle, but primarily the major or significant Bremsstrahlung you will be able to see for betas and electrons. So any charged particle you shoot of sufficient energy, and it comes in the periphery of nucleus, so it will be kind of de-acceleration. So that de-acceleration, because you have to conjure everything. So where is the rest amount? So that amount comes in terms of the photon, emitted photon. So any charged particle you shoot and it comes in the periphery of nucleus, definitely you will able to see some photons.
I
Okay,
request
sir. Sir,
yeah, I request HOD sir to give the vote of thanks because it's less than 1 minute.
Oh,
I just
okay. Thank you. Thank you, Dr. Ajay, actually for delivering very nice lecture in a very precise time. As you promised, you have finished within half an hour. Thank you very much for that.